In this video, we will understand the inner working of HashMap. But if you just want to understand how to use HashMap, then there is another video that focuses on the hands-on. It's a demo video that you can refer. But this video will simply focus on the inner working of HashMap. We will go through the documentation and we will try to figure out how HashMap works. See the source code of HashMap on the screen. Here we see when we create the HashMap, a new HashMap by calling the default constructor, then in the default constructor, all it does, it initializes a new variable load factor with a value which is default load factor. And the comment says all other fields defaulted. Also, the method comment says that it constructs an empty HashMap with the default initial capacity equals to 16 and the default factor load. So what is this default initial capacity and what is the purpose of load factor? The initial capacity or the capacity of the HashMap is basically the number of buckets that a HashMap can store. HashMap internally uses an array. So the capacity is basically the number of indexes or the size of that array. All right. The load factor is used to calculate the threshold, which means how full the internal table is allowed before the capacity gets increased. And how do we find the threshold? Threshold is basically the multiplication of the capacity and the default load factor. So in this particular case, because the default initial capacity is 16 and the default load factor is 0.75, so the default threshold is this 16 into 0.75, which is 12. So it means when we touched the value 12, the number of entries in the HashMap 12, then it is an indication to the HashMap that it needs to resize the internal table. All right. So that is the purpose of capacity and the load factor. Now, what if we create a new HashMap with a huge capacity and with a huge load factor so that it does not have to resize? In that case, if we have a huge capacity or load factor too high, yes, it will avoid resizing because the threshold will be too high, but it also means that it will increase the lookup time for the map. All right. So that is a trade-off between choosing the capacity and the load factor, and as per the documentation, 0.75, which is the default load factor, it provides a balance between the resizing of the HashMap and the lookup time. We will soon see what is this resizing of the HashMap, but for now just keep in mind that we most of the time don't need to change the default load factor. All right, moving on. So at this point, we created a new HashMap. Okay. So this is the current state. When we initialize a new HashMap, then we can say there is this internal table that will store the entries. As of now, there is nothing in this table. We have an empty HashMap. Okay. So let's call the put method and let's see what goes on in the put method. In this put method, we see we pass two values, a key and a value. It internally calls the putVal method, but first of all, it passes the key that we are trying to add to this hash method, internal hash method. In this method, we see that first of all, it calls the hashcode method on the key. If you remember from the videos on hashing and hashcode, that we override the hashcode if we plan to use a custom class as a key to the HashMap, then we override the hashcode. And let's say all the default classes, all the inbuilt classes in the JDK, they override hashcode appropriately. So whatever implementation that we have given in the hashcode method, that will be used to calculate or to find the hash of the key. So first step is to get the hash code of the key. Then it applies additional operation, XOR operation, bitwise operation on the result value, which is this one, to find the final hash for that key. All right, that hash will be used to find the location in the underlying table. That is the concept of hashing. When we need to put a value, then we pass it to a hash function. It will return a hash value, and that hash value will be the final index. And that's what it is doing here by using the hashcode method of the key that was overridden and then additional XOR operation. Okay, so we got the hash from the key. What's next? If we go to the put-val method, in the put-val method, we have the hash, we have the key, the value, then only if absent. So let's say if we are calling methods like compute if absent or put if absent, compute if present, then this boolean will be sent accordingly. It will be passed true or false accordingly. All right. So in the put-val method, the entry is actually added to the hash map. So it is important that we understand the put-val method at least on a very high level. Okay. So if we see first of all what it does, it checks the table, which is the internal table. If this table is null or if the length of the table is 0, which means the internal table is empty or null. In that case, the table is resized. The documentation of resize says that it initializes or doubles table size. What exactly is this table? This is basically an array of type node. Node is an internal class and inner class of the hash map, and it represents the entry. If we go to the node class, then we see this is an inner class and it implements the map.entry interface. So whatever we put in the hash map, it will be stored in the form of an object of class node. It represents a node. So the internal table or the internal array is of type node. So the array that we created here, it basically stores objects of node class that we saw, K and V. Okay, because this is the default case, so we can see that the new capacity is basically default initial capacity, which is 16, and the new threshold, which is the default threshold, is basically the multiplication of load factor, default load factor, which is 0.75, and default initial capacity, which is 16. So that is the new threshold. And then it checks if old tab is null. It means there are existing entries in the table and this map is being resized. But at this point, we have not added anything to this map, so it does not apply. It simply covers the case when there are entries and we are resizing the hash map. So no need to understand that. So in short, what resize method does, it either initializes the internal array or it doubles the size. This is the case where it is initializing the new array, and all other cases are to handle the actual resizing. So if there are existing entries in the hash map and we are resizing the hash map, in that case, the new size will always be the double of old size. And you can see it here that the new capacity is basically 2 times of the old capacity. This is a bitwise operation, which means multiplication by 2. And similarly, the new threshold is 2 times of the old threshold. So every time the hash map is resized, it doubles the size. Here we saw that the table has been initialized now. So a new table has been initialized, and by table we mean the array of type node. The next step is to find the index in the table. So to do that, we already have the hash key of the hash, and using this bitwise operation, we find the index, an integer value, and we go to that array and we check the value at that index and we assign it to variable p, which is node. And then we are checking if this is equal to null or not. If this is equal to null, then we create a new node and we assign that node, or we add that node to index I, which was calculated here. What it means is, if we go back to the diagram, so let's say at this point we have this array of type node, and then we are adding a new value. So let's say we are adding key k1 and v1. So the step 1 would be to get the hash of the key 1, which is, let's say, h1, and using this hash it will try to find an index. So let's say it found the index equals to 1. Now what put-val method does, it will go to the index 1. It will go to the index 1 and it will see, is there anything at index 1? And right now, if we see there is no entry at index 1, it means the node at index 1 is null. there is nothing. So what it will do, it will create a new node object, and that node object will be stored at index 1. And that's what it is doing here. So using the hash of the key, it found the index, assigned it to I variable, it found the index, then it checked the value at that index in this array, and if this is null, it means it's a new entry at that index. Then it is simply creating a new node with that key and value, and it is also storing the hash of that key and value so that it does not have to recalculate the hash. Now this is the case when at index I there is no entry. But what if there is already an entry, and which is the case of hash collision? What happens if we already have an entry at that index? In that case, what it does, it simply invokes the else part. If we go back to the diagram, here we see we already have a node at index 1. And if there is another entry that we need to add at the same location, the same index, then how do we do that? Because we already have the node at index 1. So else block handles the same case. This else block, first of all, what it does, it checks whether or not this is a duplicate entry. By duplicate entry mean, are we trying to add the same key again? To do that, it first of all checks the hash. If the hash is same, okay, then it checks the key by using double equals and equals. So it checks both the cases. If the key is same, then it means we are trying to add a duplicate key. In that case, it simply reassigns the existing entry with the new entry. So this is where we are overriding the old value with the new value. That is the case number 1 if we are trying to add the duplicate key. In that case, what it will simply do, it will update the value. So V1 will be converted to V2. Existing value will be changed to V2. It will be replaced. Okay. If this is not a duplicate entry, then the next step is to find the correct location where to add the new node. All right. How do we do that? There are two cases in the hash map, whether to add it as a node or as a tree node. So let's see both of the cases one by one. First of all, let's skip this tree node for now and go to this else block. So what it does, if we remember from the hashing video that in case of hash collision, there are two major ways to solve the hash collision. One is to use the chaining and another one is to use the open addressing. So in chaining, what we do in case of collision, we maintain another data structure, which is the linked list. So all the nodes with the same key with collision, we add those nodes in the form of linked list. And HashMap follows the same approach. So if we go back to the diagram, then it means if we already have a node at index 1 and we need to add another node, then what we will do, it will maintain a linked list. So a new node added will be here. Another node comes and that node will be added here. So in HashMap, each array index or each table index will have a linked list. It is trying to traverse the whole linked list to find the correct location. Now in the linked list, there could be n number of nodes, for example, and any node can be a duplicate node. So for each node, we have to check if this is a duplicate key. If yes, then the same logic to override the entry and the old value will be replaced with the new value. So if we don't find any duplicate and we have traversed the whole list, it means we have to add a new node to the existing linked list. That's what it is doing here. We are creating a new node and updating the next pointer of the previous node. Okay. After everything is done, after we have added the new node, at that point of time, we update the mod count and we check if the hash map needs to be resized. In that case, we resize the hash map and the size will be doubled. Okay, there is one more condition that HashMap checks. So if you notice, while we were traversing the list, we were also maintaining the bin count which is the integer variable, and which is simply the number of nodes in the list. Now if the number of nodes in the list, they breach the threshold. If the number of nodes in the list is greater than the tree threshold minus 1, and if we see what is the value of this threshold, 8, it means if at any point of time the number of nodes in the list is greater than or equal to 7, then it means the nodes or the list will now be converted into a tree. And that is an important thing to understand in case of HashMap. We know if there is a hash collision, then the new node will be added to the same list. Now consider the case when we have many collisions. It could be due to the bad hashcode method, which is not random, or maybe we are adding similar keys in succession. So what will happen? All the keys will go to the same index and it will be added to the same list, and the list will grow. And the property of the linked list is if we are trying to search an element in the list, it has order of n time complexity. So that defeats the whole lookup purpose, which means even if the hash map is faster, but due to the collision, the list is so long that it is taking order of n time to find the right value or to find the right index. So to avoid this slowness in the new versions of Java, what HashMap does, HashMap still stores the values in a list in case of collision, but after a certain threshold, that linked list is converted into a tree, same as tree map. Now tree has its own overhead in terms of complication and memory consumption, but the good thing is lookup time in the worst case, and it degrades gracefully. So that's why in the put all method, if we summarize what is happening, if this is a new entry, then we add the new node. If we already have an entry, then we try to check if this is a duplicate key, we start from the first node. Otherwise, what it will do, it will try to add the new node to the list, and after adding to the list, it will see if the number of nodes in the list breaches the tree threshold, then the whole list at that index will be converted into a tree. And that's what is happening here while adding a new entry to the map. If this has been converted into a tree, then the new node will be added to the tree as a tree node. If this is still the linked list, then it will not execute this else if, it will simply try to add a new node in the linked list. So that is the overall working of put method in the hash map. Similarly, let's go to the get method. In the get method, when we pass a key, first of all, it calls the get node method. And in the get node method, if we see the logic written over here, so if that table is not null, what it does, it first of all gets the hash of that key and then applies the bitwise operation on that hash value and finds an integer value that will be the index of that key. All right. Then it reads the value from that internal array of that index and it checks if that entry is not null. If that entry is not null, the next step is to find the right node. Because at that index, there could be a linked list or there could be a tree node. So what we need to do is we need to iterate the linked list. If the tree is there, then we need to iterate the tree and we need to find the matching key. And finding the matching key is basically simple and same as the put_val method. It checks the hash. If the hash is same, then it checks the key using double equals and dot equals. And if it finds a matching key, then it returns the value. Now, if there are multiple entries, then it checks if this is a tree node, then it will call the get tree node method to find the value of that key from the tree. If not, then it will traverse the linked list at that index and it will find the right value for that key by finding the right node in the list. The high level logic of HashMap is key driven. So whatever we're doing, whether it is get or put operation, step one is to find the hash of that key using the hashcode method. Then in the internal table, we go to that index, we fetch the entry. If the entry is not there, then in the put method, we add a new entry. If entry is already there, then we simply either traverse the linked list or we traverse the tree to find the right value for the given key. and it applies to both operations, whether it is get or put. It's a bit complicated, but I hope you get some idea about the internal working of HashMap.